Right. Hello, everyone. I'm Panagiotis Leonidakis. I'm a postdoc in KU Leuven, and I have a bachelor in physics, and then my master and PhD is mostly on machine learning. I have been working on computer vision, then my PhD is over biomedical engineering, and then my postdoc is implementing, again, the methods that I have been using during my PhD towards datasets where we have highly imbalanced data. And since in our field we are interested for rare extreme events, we have highly imbalanced datasets. So it is valid to see from the machine learning point of view how we can train our models to focus on detecting this space whether relevant extreme events. So first of all, I would like to say that in ASAP we have some use cases of how we can transport AI to onboard settings. And one of these use cases is solar structure segmentation. But before getting into it, I would like to give a small introduction of how I'm envisioning how onboard AI can change the way that missions like Solar Orbiter, how they function. So imagine that we are in the future, 30, 50 years from now. The sun is still there. I hope that we have a better understanding of the physics, of all the physics processes that's happening to the sun. But still, as a scientific community, we're craving for data, we're craving for observations. So I'm sure that we're going to have missions like Solar Orbiter, but next generation missions that could be employed with AI algorithms. And one of these AI algorithms can be possible to automatically detect solar structures like corona holes, filaments, active regions, and we can, I hope that we can identify them, characterize them. And why this would be useful? We can have a mission where we're going to have several instruments. And the bottleneck having many instruments is that we need to power these instruments, right? The main bottleneck is power. So if we can trigger individually each instrument only when we need it, that would be great. And not only that, we might need to have a high resolution telescope where we cannot capture the full disk of the sun like this screenshot, but we need to get a small segment and then capture a high resolution image. To do that, nowadays we need to carefully design, perhaps weeks or even months in advance, to carefully design the mission how we want to point a specific instrument to that area. But if we can do it autonomously, and when a specific interesting structure is detected, then we can trigger a specific instrument that is appropriate for the structure, and then capture this image, and then automatically flag this data to at some point be sent to the ground for further examination. In parallel, we can have this kind of high resolution images where we can capture like active regions, corona hole, filaments, prominences. So autonomously, we could capture this kind of screenshots without human intervention way before. But we can also have a space weather module in such a system where it would trigger a warning when some CMEs or solar flares are forecasted for the next 24 to 48 hours. Then we can pause any downlink process at that point and prioritize relevant screenshots regarding the specific areas where we think that are really relevant to the forecasted space weather events. So we can have a solar flare forecasting AI module running regularly. And then as soon as we forecast some extreme activity, then we can quickly send to the ground specific screenshots so that forecasters will be notified on ground. And then they can use, again, some AI models that are applied to be used with having strong GPUs, so we can have actually very good AI models, and then forecasters can get advice and then notify the corresponding sectors like aviation, because it might be that in a specific point of the Earth we might have some frequency disruption, and perhaps we need to deviate some planes to avoid having some communication blackouts. Or if there are ongoing flights, the pilots can be informed that perhaps in the coming 2-3 hours there might be communication blackout. So these forecasters, they are already working with AI, but they can, as soon as they can get data way before, they can have more accurate predictions. So this is how I and ASAP envisions this such an onboard AI setting. So that's why, as you know, that we have various partners, and we are, as K. Leuven, we are designing some use cases, and then we have other partners which they take our algorithms and they manage to embed it to specific hardware, and then manage to drop significantly the power consumption of our algorithms, and then we will build a demonstrator out of this, and hoping to communicate what is possible right now and what is still lacking for future missions, hopefully that would have similar settings. So, as I said, one use case that we have been designing is solar structure segmentation. And just to give a small introduction of segmentation, I would like to introduce the terms classification, segmentation, detection. So already you had some lectures on classification. So before the deep learning era, we were having images, we were extracting handcrafted features like using edge detection, like texture, histogram-based features, and then we would have a traditional machine learning method where we could classify the image and say, okay, here's the dog and here's the cat. And then after 2012, with AlexNet, then GoogleNet and all that, we have deep learning frameworks that they can they can automate this process, and we don't need to specifically design handcrafted features for specific images, but then we leave the network to the first, let's say, convolution layers to automatically extract features, and then when we have some fully connected layers in the end, is like having a classifier manipulate the extracted features in a way that we can have a final decision. And like in this example, we can have either actually the confidence of the model, how we can see how confident the model have to classify this as a dog or cat, or bird or boat. So this is about classification, extract one label for the whole image. But what we can also do, we can do segmentation. We can annotate each pixel using a specific class. So here, each pixel of this image has been classified as road, pole, sidewalk, vegetation, etc. And this kind of setting is very important, especially computer vision field for self-driving cars. So this kind of algorithms have been developed a lot from that domain, but also we have been using segmentation for biomedical engineering. So during my PhD, I did a lot of segmentation research. And in our case, we can also do segmentation for solar structure. The problem here with segmentation is a bit expensive, because imagine you need to classify, so you need to more or less do the same, let's say, process for each pixel. So a compromise is to perform detection. So we have boundary boxes, we localize a specific object, and then we classify this specific segment of the image. And then again, we can have many classes. So this is a compromise. We don't have accurate segmentations, accurate boundaries of the detected object like the segmentation, but still is something that we can be more informative than just classifying the whole image. So here is an overview of thinking that if we would be able to have unlimited resources, unlimited data, unlimited GPUs, of course, we will always perform segmentation. But when we want to reduce the computational cost, when we want to reduce the annotation effort, meaning to provide a lot of data to the training set, then we opt to go for detection or even classification. So before the deep learning era, when we would like to perform segmentation and we don't have a lot of data, we're trying to do some thresholding. And also thresholding was a very nice algorithm because it can automate this thresholding process. What do we mean thresholding? Imagine we could have the color histogram. You have an image with intensity pixel from 0 to 255. You can imagine we can always draw a threshold line, and we can classify the dark pixels as class 1 and let's say the lighter pixel as class 2 based on one single threshold. But somehow we need to automate this process because we can understand many possible thresholds, and we want this to do it without training, without anything. So auto thresholding was designed in a way where we have a grayscale image and we want to distinguish background and foreground. So in this case, for example, we want to distinguish the photographer with the background below. So if we have a histogram, you see it's very clear that we have various distributions. And the way that it works is that in unsupervised way, again, we don't intervene, we don't train, we don't annotate. We extract the histogram, and then we try to draw a line where we can minimize the within class a pixel. When we say class, we imagine we have class 1 and class 2. And also we want to maximize the between class variance. So without going into detail, that's a very nice way to have a grayscale image and automatically threshold in two classes. It's a very light algorithm, and you can find even now a lot of applications. But as you can see here, we have more than one distribution, right? So we would like to extend this to have many classes, because as you can see, we have the foreground, but we have also these buildings here that they have been classified as a foreground, but we want to have it in the background, or even a different class where we have the ground, the sky, the buildings in different classes. So again, automatically we can use multiple O2 where we have an image which we have more than two distinct intensity regions. So we actually can play with this n number, how much classes we want, and then we can again automatically draw more than one lines, have more than two classes. So if we draw two lines, we have three classes, and then we can get a segmentation like this. Again, this is a nice example where we have clear distributions in the histogram. So very easily, multi-O2 thresholding can actually detect where to design this appropriate thresholding. After this thresholding, sometimes we have some noisy segmentations. So we want to do some morphological filtering to clear a bit our binary mask. So that's why I would like to give some foundational morphological filtering for people that are not familiar. So in morphological filtering, usually first we define a structural element. So this can be this cross here, and we have four core operations: dilation, erosion, and then opening and closing, which actually is a combination of dilation and erosion. So we have first dilation. It's defined with this symbol. We have our structure element. This is, for example, your binary input image. And actually, the way that dilation works is that as soon as you have a structure element and touches or neighbors, the dark area, so the number, the one, so the true part of the image, then directly as the structure element is there going around the whole output image, it populates all as one. So in principle, it expands our mask. And erosion that's the opposite. It shrinks this area. And then we have opening, which is applied first erosion and then dilation. And then closing, where we apply first dilation and then erosion. And you can see some examples. If we can see an overview, we can understand that if we want to fill some small holes, so we have, let's say, some findings that probably they correspond to the same area, but our algorithm for somehow made some gaps. With dilation, we can join this region into one. With the erosion, we can separate objects if, let's say, the resolution of our mask is not very not high as we want. And then we can do also some opening and closing when we want to either contour smoothing or we can join broken edges. So in our application, how I actually used it is it as I played with the various combinations and then I found the best setting. So we can define such an algorithm. So this is an algorithm that I proposed in one paper. It's very, very simple, which I call basic computer vision operation. So we can have our input image coming, for example, from SDO 193 AIA. Then I first apply multiple O2. Why I wanted multiple O2? Because my first goal was to segment active regions, which are high intensity pixels, and corner holes, which are low intensity pixels, right? So I want first to get segmentations of the active regions and then some segmentations of corner holes. And then I get two masks. And after getting the output from multiple O2, I wanted to clean a bit my mask, not to have a lot of noise. And I wanted to merge my findings as well to have clean masks. And then that's why I opted for some morphological filtering. And then in the end, the output of this algorithm can have the bright areas, which is mostly active regions, but unfortunately also some lit brightening if I haven't pre-processed properly my input image, and then some corner holes. On this, we can have a hands-on exercise in the afternoon where you're going to actually play with multiple lots and play with some morphological filtering. And I'm going to show you how actually to acquire an SDO image directly from JSOC, pre-process it a bit, and then play with this and actually create a pipeline of your own version. And then you can play with morphological filtering with various combinations of opening, closing. You can actually see in practice how this post-processing can be done and how it can be tuned. So let's move to object detection, because as I said, segmentation can be really heavy if you are having neural networks. Unfortunately, an algorithm like BCVO has been designed to work in a general CPU purpose hardware settings. So if we want to use hardware which we could drop the consumption and we could accelerate the performance, we should opt for neural networks. That's why I wanted to present an algorithm where it could take a lot of data obtained by BCVO and then train a neural network to perform either segmentation, either object detection. So first, let's talk about deep learning based object detection. So a bit of history. After AlexNet, what was presented, performing classification, people said that, okay, we can run multiple times AlexNet through segments of classes. So the question was that first you take the input, you have a first, let's say, agnostic detector where you can extract region proposals. So this is the first big step of this algorithm. And each segment, each part of this image can get forwarded to a classification algorithm like AlexNet. And then you classify only the segment as a cat, dog, or airplane, here, person, etc. So in the end, you can have object detection output. But as you understand, this is kind of expensive, a bit. It's silly to have too heavy algorithms to run one after the other. And then fast and faster RCNN were proposed to somehow automate the process and accelerate the region proposal mechanism, and then we were able to extract first the segments, and then all together to run only once the classification, and not each time run the classification head again and again and again. But again, we had two algorithms every time for one image. So then you only look once was proposed, and it was named like this because automatically it was creating a grid, either 4x4, for example, or 8x8, etc. And then with only one pass, like the classification algorithms work, they can both extract bounding boxes and characterize them with a classification head. And we can have the final detection. And the first version was a revolution because you could do object detection just in using one network. And then since then, there is version 2, version 3, and now I think we're at version 11 or version 13. You have to keep track of these things. And not only that, they since they were aiming to offer to the community small networks with a very limited amount of parameters, they provide, let's say, the version 8 that I have been using was providing even a nano version, which was the one that I was using, but it was very, very light. Of course, it's not very accurate as the main model, but since it was trained in a lot of data, you can use you can fine tune this model using transfer learning. So you can train the whole model on ImageNet or Coco, and then you can take this nano model and fine tune on the last layers just for your application. And this is what I did for my work. So this is the version 8 nano. So it's a straightforward network, and in the end, it has a regression head and object classification in the end, and also since YOLO is having a lot of bounding boxes, there's a head to evaluate if this box is actually meaningful to be extracted or not. That's why you have the bounding boxes coordinates, the probability of this box to have a meaningful object characterizing, and then the characterization, which is the class. And of course, you can post-process this output, setting a threshold, how much confidence you want to visualize to your final output or not. Remember, yesterday we had such an example. And in parallel, I wanted to examine how how expensive can be the segmentation using deep learning. And then the main networks that are presented performing segmentation are called UNet. So we have the image, the input image. A first part is called encoder, which looks like the classification networks like AlexNet, but we don't end up to just one decision, but to a small feature map. And when I say small, it's many channels in the third dimension, but small in the 2D, right? And this we call it bottleneck. So here we extract all the meaningful features that we want, and then we need to somehow go back to the original form of the output, but in a form of probabilities or a mask. So that's why we again to minimize the third dimension, the channels, and then again the feature map need to grow until we end up to the resolution of the input. So UNet was actually first proposed for biomedical engineer because we have modalities like CT, MRI, X-ray, etc., and we want to extract boundaries of structure like organs, let's say for MRI when you have the full body MRI. But since then, it has been presented in various applications. So yeah, I explained decoder, and sometimes if you have the encoder, the bottleneck, and then the decoder, you lose some valuable information, and that's why we somehow we also include some skip connections in order to have increased resolution in our output. This is a designing decision because if you want to be able to retain a lot of information here, and if you're opting to extract meaningful features and then be able to reconstruct only with this bottleneck, then you don't want to have these skip connections. Like in a very similar setting, we have the autoencoders. I'm not sure if you had lectures on that, but in this case, where we want to have accurate segmentations, then we want to have increased resolution and we want to have the skip connections. So in this, taking the UNet, there is in 2021 it was proposed the SSNet, Solar Coronal Structure Segmentation Net, where Maskowiak and authors proposed two models, one model performing active region segmentation and one model performing coronal hole segmentation. And you can see it's a very standard UNet architecture, which used, again, SDO data and various sources of annotations and managed to propose two very accurate models. And then as soon as we have segmentations, either from SSNet, either from the BCVO, what we can do is that we can isolate our segmentations, and from each segment, we can extract various features, handcrafted features like contour, like texture, intensity, histogram-based features. Then we can perform feature selection using, for example, correlation matrix, where we can see all this. If we have, for example, 30 or 50 features, we want to see how many of them correlate with each other. So we should not replicate the represented information. And then after doing this feature selection, we can use unsupervised algorithms like k-means. So we can characterize our findings so that our output image would actually represent each cluster with a different color. So this is an overview of all the architectures and systems that I had in mind, that it's relevant to compare, to improve, and to see how we can apply to our use case. So here you can see how SSNet can extract coronal holes, how YOLO can detect, for example, active regions. So for YOLO, there was not any model for solar structure segmentation, but what I did is that I took the proposed dataset from SSNet, they released the models and they released their dataset. So I adapted the annotations towards bounding boxes and not accurate segmentation. This is something very easy to do. And I retrained my model, the version 8 nano. And again, following the SSNet models, they had two models, one for active region, one for coronal holes. Then I developed two models, one for active region and one for coronal holes for YOLO. And in parallel, I have my unsupervised system where I can threshold my segmentations and in parallel characterize with the unsupervised method like k-means, as I said, or TSNE. And then here, for example, we can get some active regions characterized based mostly on their area. And then some coronal holes, again, we could differentiate some filaments and coronal holes. So the question here is how we can compare these methods and see which method is more applicable for AI on board setting, which method is more applicable to be used on Earth under a setting where we have a lot of computation power available, which method is appropriate to generate a lot of data if we want to fine-tune these two data-driven solutions. So my first criteria was to compare the algorithms on-board suitability, and as expected, YOLO was very easily decided that this is probably the best setting, because if you see the amount of parameters needed for SSNet to train and to deploy, you have 78 million parameters, and the YOLO version 8 nano, 3.2 million parameters, so a drop of 90 to 95%. As I said, BCVO is a very light one, but we cannot really parallelize it. We cannot really optimize it to have it in a special hardware, in programmer hub hardware. So BCVO, this setting is not so much applicable. However, in our mind, we have the idea that probably SSNet is more accurate. So we still need to investigate how we can simplify SSNet, and in order to reduce the amount of parameters, but still be able to perform segmentation that, of course, should provide better results than just detections of YOLO. So here I would like to provide some implementation details of SSNet models and YOLO, since I did the same split and dataset. So from SSNet, they tried to find various annotation datasets. So the first one was SPOCA, but it's actually you can also use it Helioviewer that Katya presented before. So all the SPOCA masks can be retrieved either via online API service from ROB, from Brussels, from Royal Observatory of Brussels, or you can visualize it using a heck model in the Helioviewer. But the problem with SPOCA is that it's very, very conservative. So if you have a big corona hole with very nice boundaries, but you lose some, let's say, segmentation accuracy. So we'd like to have a model that is not so much conservative. So then they included data from Chimera, another segmentation algorithm that takes, as SPOCA, information from various SDO wavelengths. And Chimera tends to over-include. So if you have a corona hole and a filament along, you're gonna all get a characterization as corona hole. It's something again that you don't want, but providing these different behaviors, you hope that the model will be able to generalize and provide something in between. And region growth, it's again another system provides some masks for corona holes, and they also did some manual annotation. So they had a group of students, mostly master and PhD students, who got an online tool and were able by hand to annotate structures like activation corona holes. So they created a very nice data set. They used data augmentation. They have generate even more samples. And they have these two data splits for active region model and for corona hole model, which I also followed in order to benchmark my results with their findings. How we benchmark? The main evaluation metric was die-score, which actually is being used mainly a lot in biomedical engineer segmentation. But I also used intersection over union, which can be very easily applied for detection for YOLO, for example. And also per structure, we can characterize which structure we're losing or not. So then that's why we can also use precision and recall. And this, we'll have a bit strict, let's say, metric. This is MIAP at 0.5. What does it mean? Is when we have intersection over union more than 0.5, then we can calculate the average precision. So these are some findings. So if I just visualize what I found only using die-score, and let's go to this graph. So first, let's see the graph on the left. For each different color, I have, so the blue is as SSM models, the yellow is the YOLO models, and the green is the BCVO. And the first column is for active region models, and the second for corona holes models. So you can see that SSNet is significantly providing better performance. But we have to be critical here, saying that SSNet is doing segmentation. So we shouldn't compare segmentation with detection. So that's why the output of the SSNet, I adapted as boundary boxes, and then I reevaluate my systems in order to equally present my results compared to YOLO. And the same I did also for BCVO. Again, I converted the masks to boundary boxes. And we can see in this graph now performing only detection that all the three systems, they perform well, and they provide similar performance, meaning that actually YOLO provides a good compromise for onboard setting and also a good compromise in terms of performance. And of course, BCVO can qualify to provide high quality data if we want to create even more data to train YOLO and SSNet. Our third criterion is to examine an event and see how we can actually, how accurately we can detect this coronal hole and how we shouldn't at some point detect the filament. But if you see this event, at first they have a filament, but then it becomes one with a coronal hole. So that's an interesting event, and we want to see the behavior of our segmentation model. So if you see the Spokai masks, you can see that it's very conservative. So in my case, I would like also this part to be part of the coronal hole segmentation. But it does well here that it doesn't apply here. Mask doesn't say that it's a coronal hole because it's a filament. Chimera, on the other hand, all the dark areas says, okay, this is a coronal hole. So we have these two big extremes. And here I have an example of how multiple O2 segmentation works. So we have the input image. I run multiple O2 for 5 classes. The fifth class is the darker class. So you can see how well the fifth class represents the coronal hole. And if I take only the fifth class and run morphological filtering to remove all this noise, I get this nice mask where I can get very nice boundary boxes, better than Chimera and better than Spoka. I have included here, but SSNet tends to be a bit closer to Spoka, meaning that it was something like this. But in practice, if we know that we can even improve and fine-tune SSNet, providing data from BCVO. Why doesn't it go? Okay. And then another application that we thought that it's very important to investigate and compare our methods is that we want to use AI on board, right? So we should use data captured by our spacecraft, and directly this data should be forwarded to our AI model. The problem here is that usually how SDO works is that we take the level 0 data, the raw data, we get them onto the ground, and then on the ground we get some values in order to be able to calibrate the data and we get as researchers a level 1 data, and then this level 1 data that we get, we pre-process, we normalize the pixels and all that, and we make our images appropriate to be used for machine learning applications. So we call them, let's say, level 2 data. So my models actually have been trained on level 2 data. So we want to see how the level 0 data that's what potentially is available to our models, how this data, how these samples are compatible with our models. And if we managed to get for the SDO case, some level 0 data, and with a very simple ways, I tried to normalize the pixels and all that. So here is the original fit image with a lot of noise, 4K by 4K. With a very simple min-max normalization, we get this image, which is, we were expecting much more noise. So in case of SDO, we don't have so much noise, but it's clear that we have, for the full disk image, we have 4 distinguished quadrants, meaning that we have 4 different acquisitions. So if I provide this image to the network, it will not work because each quadrant has different intensity distribution, and the models have not been trained to be able to understand this kind of images. So we want to provide a normalization pipeline, which is light enough to be included on board, but at the same time to overcome this quadrant discontinuity issues. So after playing with many light pipelines, we came up with the idea that it's very close to what actually it's been done on the ground. So we calculate the min-image of each quadrant and the min-image of the whole. So for each quadrant, we added the overall mean values and then subtracted the overall the specific mean of the corresponding quadrant. And with this relatively light operation, we managed to get rid of these discontinuities. And then, as you can see, this image looks very close as level 2. And we tested with some data that we got. And we managed to see that our models perform relatively the same, actually, compared with level 2 test set. So without any fine tuning, without any other difference in our pipeline, by just doing this light preprocessing, we managed to get the same behavior. So our answer here to our question is, are our models compatible with level 0 data? It's yes, under this light normalization process. So here we even tried, we did some tests without doing the very specific normalization. We were curious a bit to see how these discontinuities were affecting the models. So for the active region model for SSNet, this is I think, yeah, for SSNet, it was okay. But for the Corona Hall, actually it was getting only in some results only for one quadrant. But of course, when we apply the normalization that we proposed, then all the findings were correctly segmented. So those are findings have been published recently to a paper, and we provide the YOLO models online in the GitHub directory, and also this normalization steps for the level 0 data. We also have them available online. And remember, we have in our mind still that SSNet should be able to be reduced, so to be simplified in order to provide some segmentation. So I proposed this topic to a master student that right now he's defending. He has already submitted his thesis, and we hope that after his defense, we will also publish our findings. So I proposed him to get this non-new UNet framework, which has been used a lot in biomedical engineering field, and see if he can create a new SSNet model. What's the difference in non-new UNet? It examines various settings of input resolution, different kernels, and automatically finds the best balance between how heavy or light the model should be and how accurate should be our findings. So automatically adapts the model hyperparameters in a way that we can have potentially a simpler model, a UNet model simpler than SSNet. And at the same time, I propose that we should include also filaments. And also I propose that we should have multi-label segmentation, not to have a dedicated model for each structure, one model for active region and one model for Corona holes. So overall, I was opting to get one model, a very light model, performing three label segmentations, one for active region, one for Corona holes, and one for filaments. And at the same time, explore to have it as an input, not only one wavelength, but various SDO wavelengths. So it was a big project, and Roman managed to get it through all of it. So we can see here some small networks that imagine here in millions. We can remember we were 70 million parameters with SSNet, and he managed to have a model with 2.5 million, 1.5 million, or even below 1 million to have 360K. And we also here, the bottleneck was that we needed filament data. So manually, we created a small data set using H-alpha observations. So Roman annotated a lot of samples using filaments from H-alpha and created his ground-truth mask. So that this is an example of ground-truth mask, which has Corona holes, active region, and filaments. And this is some findings that were related to the image. And we provided to our partners from ASAP, we provided some models, again, to cater for different departments, they are using FPGAs. So we managed to run these algorithms to dedicate hardware, and we saw that this part here, which is the inference of one sample, it has consumption around 5 to 7 watt, which is very good because we are opting to have it something below 10. Your GPU, you would be in a regime of 100, 500 watt. And optimally, we would like to aim something between 2 watt, but that's a bit more, let's say, ideal. We're not there yet. But having as a model between 5 and 7 watt indicates that these models have the potential to be implemented in such hardware configurations. So thank you for your attention. I'm open for questions, and here is also this QR code that it's our recently published paper. Do you have any questions? Yes.
What can current spacecraft do in terms of wattage? What current spacecraft hardware is state of the art one?
Yeah. So as I said, if we had the possibility right now to launch a dedicated hardware spacecraft with our algorithms, we should have algorithms below 2 watt.
Okay.
But we're not yet. I mean, this hardware has to be checked that it's trustworthy to be sent in the space, this hostile environment. So unfortunately, we have to innovate more in terms of software and hardware.
As a reference, and don't quote me on these numbers exactly, but I think JUICE has for all the instruments like 36 watts to use.
Yeah.
But it's all instruments.
Yeah.
Mm-hmm.
Including also how to operate the thrusters, right? Because you need also some.
I think the 36 watt was an instrument.
Instrument.
Yeah, only.
Oh.
Possibly.
Yeah.
But don't quote me on the exact. But it's on those ballparks.
Is it a kind of a dedicated chip for this? How is it implemented in real spacecraft? Is it a dedicated chip or?
Yeah. So in real spacecraft, we don't run AI at the moment, and that's why our partners want to design a chip where actually all the networks and the weights are hard coded to the hardware, so that we don't consume energy to load for the memory of the weights all the time. So to avoid having to transfer data, which again is expensive in terms of power. So we want to design our algorithms to the hardware. So we have a special chip only for our use case, and then this chip, then we can measure power. We can measure what kind of cadence can offer, and
field programmable gate arrays, FPGAs. They are specifically designed for your algorithm, so they are different than a GPU in the sense that GPU is multi-purpose. You can put whatever you want, all kind of networks.
Yeah.
In this case, you would build like a network that is built specifically for this algorithm. You could uplink the weights, so you could change the weights and respond like this in the situations. But it would be a coded network.
Okay.
Yeah.
Yeah,
and they are already using it not only for networks; they are using it actually for, their applications for FPGAs, other types of operations that you would do in space.
Yeah. Imagine we're using FPGAs because economically, financially, it's not profitable and it's not realistic to design only 1 or 5 dedicating one chip. But if we would like to have this prototype printed 100 to 1,000 times, then you create an actual chip.